We will now start talking about the nearly free electron theory, which is the band theory of solids. Now, what was wrong with the free electron model? It was very good in explaining heat capacity, thermal conductivity, electrical conductivity, etc. But it fails to explain the difference between metals and semiconductors, and there are some anomalous results like positive Hall coefficients in the Hall experiment. So to explain these results, we need a more sophisticated model which takes into account electron lattice interactions, and the band theory of solids is basically aiming to solve these problems. As the electron moves through the crystal, it travels under the influence of the potential well of each ion on its track. We talked about this. And the reason we thought that the free electron theory was good was because the time an electron spends in the vicinity of an ion, of this potential well, is very short because it accelerates as it approaches the ion, and therefore we could treat it as a free electron, and also the electron-electron interactions were unlikely. Now, Bloch in 1928 approached this problem by saying that the electrons of a solid actually belong to the crystal rather than an atom. So we should consider the electrons to be part of the crystal. And if a potential is periodic, so we have these periodic potential wells as we travel through the lattice, in one dimension we will have B of x is equal to B of x plus a. The solutions of the Schrödinger equation must have wave functions, so we should have traveling waves, e to the ikx, that are weighted by a function of x, uk of x, so it's a function that depends on k. These are called Bloch waves, and this function uk of x takes care of the periodicity of the lattice. uk of x is equal to uk of x plus a. Okay, so these are called Bloch wave solutions. So it's very important that these solutions have this form for the periodic potential problem in Schrödinger equation. Now, we can start with a Kronig-Penney model. One approach to deal with this problem was proposed by Kronig and Penney in 1931, and this model analyzes the motion of an electron in a one-dimensional array of square potentials. So instead of having this parabolic potential shape, we can think about square potentials that have width a and separated from each other by a potential barrier of height V0. So we have these periodic square potentials. The potential width is B, so you can see here this width is B, and the height of the potential is V0, so the potential barrier is V0, and they are separated from each other with the distance a. So you can see here the potential barrier width is b, and the potential barriers are separated by a distance a. So when we solve Schrödinger's equation for such a problem, there are two distinct regions we need to consider. One is the region between 0 and a. So in this region, we are inside the potential well. The potential is 0, so the electron is free to move. So we have particle in a box solutions, basically. The second derivative of phi with respect to x plus 2me over h bar square phi is equal to psi is equal to 0. This is the Schrödinger's equation. So we have written Schrödinger's equation for v is equal to 0 case, and the solutions are of the form a e to the ik1x traveling wave solutions plus b e to the minus ik1x, so it's traveling to the right or traveling to the left. And this k1 wave vector is related to the energy. K1 square is 2me over h bar square, because the energy is that of a free electron. Energy is h bar square k1 square divided by 2m, which is purely kinetic energy. So this is epsilon k. Now in the second part, between minus b and 0, so this is inside the square potential. Potential is v0. For bound state solutions for energy less than v0, we write Schrödinger's equation for the case where we have potential is equal to v0. So we have d squared psi dx squared plus 2m over h bar square e minus v0 psi equals 0. The solutions are exponentials, c e to the k2x plus d e to the minus k2x, where k2 square is 2m over h bar square v0 minus e. So when e is less than v0, what do we have here? We have a positive value, so k2 is going to be a real number. When e is greater than v0, we will have unbound solutions, so then we will have traveling waves. Now, we have two types of solutions in region 1 and region 2, and they have to match at the boundaries. So boundary condition is that the wave function is continuous at x equals 0 and x equals a. So we're looking at two boundaries of region 1, and their derivatives must be continuous at x equals 0 and x equals a. So if we write down these conditions at x equals 0, a e to the ikx plus b e to the minus ikx becomes a plus b, and c e to the kx plus d e to the minus kx becomes c plus d. So a plus b is equal to c plus d. When we take the derivative from a e to the ik1x, we will get ik1a, and for b e to the minus ik1x, we will get minus ik1b, because we're substituting x equals 0, e to the x gives us e to the 0. And for the second region, we will have k2c minus k2d. So k2c minus k2d. So we will obtain ik1a minus b is equal to k2c minus d. And then we look at the other boundary, x equals a. So that is this boundary here. And here we will have a e to the ik1a plus b e to the minus ik1a is equal to c e to the k2a plus d e to the minus k2a. The wave function is continuous. The derivative is continuous. ik1a e to the ik1a minus b e to the minus ik1a is equal to k2c e to the k2a minus d e to the minus k2a. So there are four equations and four unknowns, four coefficients a, b, c, d. These equations are homogeneous and will have a non-zero solution when the determinant of the coefficients is 0. So we write the first equation, a plus b is equal to c plus d, 1a plus 1b minus 1c minus 1d equals to 0. So that's the first row. And then second row, ik1a minus ik1b minus k2 c plus k2d is equal to 0. So we're taking the k2c minus d to the left hand side, and so on and so forth. So we do this for x equals a boundary conditions. So we obtain this determinant. And the determinant of the coefficients must be 0. So that gives us four equations for these four unknowns, and we can solve for a, b, c, and d, which is a tedious job. Now, if we assume solutions in the Bloch form, we have an additional requirement. So we have Bloch wave solutions, uk of x e to the ikx, where the wave function is periodic. So uk of x plus a e to the ikx e to the ika. This must satisfy uk of x equals u to the uk of x plus a, plus we need to have e to the ika satisfying the periodic boundary condition. So the e to the ika must be equal to 1, right? So that means we should have cosine ka plus I sine ka equal to 1. When is that possible? When ka is equal to 2 pi, for example, cosine 2 pi is 1. When ka is equal to 4 pi, it will be 1, etc. So we will have k is equal to 2 pi over a. So we will have this requirement. Now, when we write this condition for the solution between a and a plus b, so if we go here, between a and a plus b, we should have the same thing happening between minus b and 0. So it's inside in the same region, in the second type of region, we will have psi of minus b x to 0 e to the I k a plus b. So I go from this, basically I go from here to here. I should have the same solution. So this is going to be the same solution when I go from one side to the other side, e to the I k a plus b. So that means we will have psi between a x and a plus b is a e to the I k 1x plus b e to the minus I k 1x, which is the solution in the first region. So we're going from the square well to the square well. So this is actually not right. So we should have here. So let's correct this one. We should have here the same solution, c e to the k2x plus d e to the minus k2x, this solution here, which is translated by a plus b, so e to the I k a plus b, the solution inside the square well between minus b and 0, that belongs to this region 2. So that is the solution here, so that's the solution. So this is going to be multiplied with e to the I k a plus b. So that is going to give us another condition on these solutions. So we have a, b, c, d determined from this coefficients, determinant of the coefficients becoming 0. And then we have another condition that the solution is periodic and it obeys the Bloch functions. And that gives us, in a tedious calculation, that gives us the following equation: k2 square minus k1 square over 2 k1 k2 sine hyperbolic k2b sine k1a plus cosine hyperbolic k2b cosine k1a is cosine k a plus b. So this is what we find when we apply this Bloch wave form to these solutions, and that relates the k1 and k2 to the k wave vector of the Bloch wave. Now, in order to simplify this result, what Kronig-Penney did was they assumed that these barriers are treated as delta functions. So what is the simplification in that case? These V0 values, finite barriers, become infinite. V0 goes to infinity. The width of the barrier, which is b here, that goes to 0. So b becomes 0, but at the same time, V0 times b, the area of the barrier stays finite. So this area inside the barrier, this area should be staying finite. So that's how we obtain the delta function. Okay, so with that, sine hyperbolic k2b, which is e to the k2b minus e to the minus k2b over 2. Now, b is becoming 0, so we have e to the x for small x, e to the x for x equals to, almost equal to 0 is 1 plus x, so we have 1 plus k2b minus 1 minus k2b over 2. Ones cancel, so we obtain k2b. For cosine hyperbolic k2b, we obtain e to the k2b plus e to the minus k2b. That gives us 1 plus 1 over 2, which is 1. So cosine hyperbolic is replaced with 1, sine hyperbolic is replaced with k2b. So that's what we do in this solution. k2 square minus k1 square divided by 2 k1 k2. So we have K2 when V0 goes to infinity and B goes to 0, K2 is much, and we also assume that K2 is much greater than K1. So that's basically what we have here. K2 is much greater than K1, so that we have a strong decay in this potential because it's an infinite barrier. So we will have K1 neglected, so K2 square over 2 K1 K2 K2b sine K1a plus cosine K1a. So that gives us K2 square K2b divided by 2K1. So I multiply top and bottom with a, so it becomes BA over 2K1a sine K1a plus cosine K1a. This is equal to cosine Ka plus b, but because b is 0, it becomes cosine Ka. So we can see that these solutions should be, because they are equal to cosine Ka, it should be between -1 and +1, and K should be n pi over a as b goes to 0. So we have energies h bar square k square over 2m in the infinite well. So if you say that P is equal to K2 square BA over 2, then we can say that these solutions have this form: P divided by K1A sine K1A plus cosine K1A equals cosine Ka. So what this tells us is that not all K1 values are allowed and not all energies are allowed. There will be energy gaps for Bloch-like solutions to exist. So let's see that. So this is the figure from Kittel. So if you plot P over K1A sine K1A plus cosine K1A equals cosine Ka, so the left hand side is plotted here for P is equal to 3 pi over 2, and you can see that there are regions where this solution exceeds +1 and -1, so they will be excluded from the solution, which means that not all K1 values are allowed. So K1 values, for example, that are in this range are not allowed, in this range are not allowed, not allowed, not allowed, not allowed, not allowed, etc. So this is an interesting result, and the corresponding energy, which is h bar square k square over 2m, will have these gaps in the solution. So for k is equal to pi over a and 2 pi over a, 3 pi over a, etc., we will have these gaps in the solution. So this is going to be the result of not allowing these solutions in the epsilon versus K1A plot, because they must have Bloch-like forms. So Bloch-like solutions suggests two results. First, not all K1 values are allowed, and second, not all energies are allowed. There are energy gaps for Bloch-like solutions to exist. Okay, so we have gone through the arguments why we need this nearly free electron theory. Well, first of all, it's because there are experimental facts like positive Hall coefficients and the difference between metals and semiconductors we cannot explain with the free electron model. The band theory is based on Bloch-like wave functions, where Bloch suggested that the electrons belong to the crystal, and the wave functions are of the form u of x e to the ikx, traveling waves that have a periodic function up front, uk of x, that takes care of the periodicity of the crystal. Kronig-Penney model basically treated this problem by assuming we have a periodic square potential where the width of the barriers go to 0 and the height goes to infinity, while the product stays finite, which is the recipe to obtain delta functions. So these delta function solutions, we first started out with assuming finite barriers, and we looked at the boundary conditions, where we assume that the wave functions and their derivatives are continuous at the boundaries. That tells us what the coefficients should be in the solutions. In the zero potential regions, we have free electrons, so traveling waves. Inside the barrier, we have decaying solutions. So we have c e to the k2x plus d e to the minus k2x exponential solutions. And if we assume that these solutions have the Bloch form, then we write for the periodicity requirement psi of x between a and a plus b is equal to psi of minus b x between minus b and 0. So inside the square well, for example, we require the same solution. Then this gives us an equation for the Bloch waves, which is an equation between k1, k2, and k vectors, wave vectors here. And in order to simplify this result, as we said, we let the v0 go to infinity, b go to 0, and v0b stays finite. That is the delta potential, and k2 value is much greater than k1, so that we will have a quick decay inside the delta potential, where it should go to 0 actually. So sine hyperbolic k2b is k2b, cosine hyperbolic k2b becomes 1, and with that we obtain, for the right hand side, cosine ka, for the left hand side we obtain an equation that contains k1 only. And by looking at the solutions for these Bloch-like Bloch waves, we find that if we plot this left hand side versus right hand side, the energy values will be limited to certain regions. So only certain k1 values will be allowed, because the solution cannot exceed +1 or cannot go below -1 because of the Bloch requirement. So here's our Bloch requirement. And therefore we find that we have energy gaps. So if we write h bar square k square over 2m, we find energy gaps at the Brillouin zone boundaries, basically. K is equal to pi over a, 2 pi over a, 3 pi over a, etc.